Science time. Please try to be quiet. Science time. We're going to talk today about, I'm going to call this one fossils and relative age dating. Now, I'm going to call it fossils and dating because we're also going to talk about absolute age dating. And I've made this joke before. We're not talking about dating like, you want to go to homecoming with me, that kind of thing. I'm talking about the age of a fossil or another earth material. We had talked about this before. Okay, and so we had been over last time that fossils can be formed in one of many different ways, right? And are fossils very common? Would you say 50%, 75%, 10%, or 1% of organisms are fossil? And none of those is right. 1%. But yeah, the nearest would be 1%. The very, very, very few organisms are fossilized. Very, very, very few are fossilized. So that makes fossils even more important. Let's get started. Okay. So the first thing we're going to talk about today is, and all of this relates to fossils, but we're going to talk about dating of sedimentary rock layers. So dating of sedimentary rock layers. This also applies to some extent to other kinds of rocks. There are three main kinds of rocks. Sedimentary is one. I've written that one. What are the other two? Does anyone know? Will?
Igneous.
Igneous is another one. And Ty? Metamorphic. When did you learn these, if you don't mind my asking you?
6th grade.
6th grade. Okay. Okay. Gunnar.
So, wouldn't there be more fossils as the years go on? Like the percentage of animals being fossils?
I would say you're probably right. The question was, would there be more fossils in, I'm going to paraphrase and say, would there be more fossils in later? Yes, because, not just because there's more, I wouldn't say that there's more organisms that get fossilized. There's probably even less now than ever. But the old fossils, the oldest fossils, are also subject to the rock cycle. So as the rocks that those are in get recycled in the rock cycle, then those fossils are gone too. And so it's rare to find the oldest fossils. And for another thing, the oldest fossils are single-celled life forms, so it's kind of hard to find them anyway. But the oldest fossils are rarer than younger ones. Yes. Will.
What if you found a fossil that you could tell it's 9,999 years old, and then a year passes? Would you have to give that in?
That's the kind of question that, I think that's awful specific. Well, I would say that if we found a fossil, if we had a magical ability to, like, if we could say, fossil, how old are you? And it said 9,999 years and 364 days. And the next day we asked it, it said, oh, I'm a fossil now. No, it's not. 10,000 years is not the cut. That's kind of a general rule. And usually when we date fossils, as we're going to find, it's a pretty loose science. I mean, we can date them to within 5,000 years is about the best we can do. But when we're talking about things that are 65 or 250 or 350 or 1 billion years old, then 5,000 years is almost nothing. You see what I mean? So with the like 10,000-year-old fossils, we're talking about things like really recent mammoths, and usually those are like human excavations. Like we're talking about Australopithecus or ancestors of man, and less about other organisms. Hunter.
So is bones fossilized before they hit 10,000 years old?
I don't know. It depends on how the length of the time that it takes to fossilize something varies. The permineralization probably can easily take longer than that. And you know, there's grades of it. So like a bone could be partially permineralized, where it's still mostly bone, but some of it has been replaced with minerals. Excuse me. That'll be a nice sound for the video to have in it. Just germs hitting the micro diaphragm, and you can hear every individual germ screaming as it does so. Okay, so we're going to talk about this dating of sedimentary rock layers. There are several rules to what we call relative age dating. This is I love this phrase because all the little, in the midst of puberty 8th graders are like, I don't date my relatives. But we talk about relative age dating, and I'm not talking about your relatives, and I'm not talking about you dating them, although I would recommend against that, even though we're in Nebraska, even though we're in Crawford. I would recommend against that. But we're talking about, what does it mean? What does this adjective relative mean? What's another way we could say that? So we know that a noun, a relative I have, a noun, would be someone who is what to me? Related to me. And so this adjective relative means as it relates to. So we're talking about the age as it relates to something else. So relative age dating is like, I am older than Ty Anders. And that's the truth. And it's relative age dating. Because what am I doing there? I'm what? What verb could I use? Yeah, I'm saying my age, and I'm not saying that what my specific age is. I'm saying this is my age as it what's to Ty, as it relates to Ty, as it compares to Ty. So we could call this comparative, comparative or comparative. I don't know. Look it up later. I don't really care. Comparative, which means that I'm comparing the ages of things. I'm not saying this fossil is, when we apply it to fossils, I'm not saying this fossil is 190 million years old. I'm saying this fossil is older than this fossil. You with me? I'm not saying Kesslin is 13. I'm not saying Kesslin's 13, but younger than Ty. Are you? No, she older than Ty. Whatever, I don't care. But you see what I'm talking about. I'm not saying, as opposed to absolute age dating, as opposed to absolute age dating, which is where we ascribe an actual numerical value. An actual numerical value to age. So this would be, the T-Rex fossil is 67 million years old. That would be absolute age dating. The T-Rex fossil is older than the mammoth fossil. That would be relative age dating. Do you see the difference? Do you have questions about these two things? Mammoths went extinct, I think, about 5,000 years ago. The fact there were mammoths roaming the earth when the pyramids were being built in Egypt. Oh, really? So there were human beings. There was overlap between those. But there was not overlap between human beings and dinosaurs.
So there are still, like, mammoth bones in the ground that aren't fossilized?
In fact, this is not what this video is about, but there's a mammoth was found, original soft parts preservation, because it was frozen in the Siberian tundra or something, and at the little exposition they had for it, they cut up chunks of the meat and made stew out of it. So they had mammoth stew. For the first time, human beings had that extinct, because human beings would have eaten mammoth stew before. They thought it was gross, yeah. Okay, because it was old. It was super. I mean, it was 5,000 years old. Anyway. You have questions about this? I want someone to raise their hand. They're going to give me an example of each of these from your little personal lives. Think of one real quick. Okay, Gunnar. Which are you choosing?
Absolute.
Okay, Gunnar is going to give us an absolute age of something. Let's hear it, Gunnar.
I am absolutely 3 days older than Kesslin.
Okay, that's still relative, because you're talking about how you're older than Kesslin. It's still relative age dating, even if you have a number of years.
13 years old.
So absolute age dating, and you don't know this applies not just to people, right? You could say this can of green beans was produced 2 years ago. It is 2 years, 4 months, and 1 day old. That would be an absolute age dating.
This is going to be right this time.
Okay.
I am absolutely 13 years old.
Good. Oh, here's the other thing. You know that this doesn't mean exact, right? Don't be confused between this. This is not equal to exact. This doesn't mean it's exactly 67 million and 0 years old. It means that is a number age. It doesn't have to be usually not very precise at all. It's hard to get fossils to have a precise age. And furthermore, it doesn't really matter what the precise age down to the minute of this fossil is. We're just only talking about how many years old it is with any amount of precision. Kesslin.
I'll do absolute.
Okay, Kesslin's going to give an example of absolute age dating.
I am exactly 13 years old and 23 days.
Beautiful. But you know that it doesn't mean it's exact, right? Like you could say, I'm 13 years old. You could say, I'm 20 years old. And even if it's wrong, it's still an absolute age. Do you see what I mean? Absolute does not mean it's perfect. It doesn't mean it's right. It means that it's numbers. Am I making sense here? And then, so what's an example of relative age dating, Gabe?
Whitney is a week older than me.
That would be an example of relative age dating. Whitney is older than me.
Whitney?
I'm older than this book. I'm older than the book. That's relative age dating. This book is older than this pin. That's relative age dating. It doesn't have to be people. And it doesn't, but do you understand that this does not mean exact? It doesn't mean that it's a very precise amount of measurement. It just means that this one, basically, this is it. Numbers is absolute age dating, and comparisons is relative. It doesn't even mean they're right. It's just that it's comparisons if it's relative age dating, and it has actual numbers if it's absolute age dating. Yes?
This school is older than every living person on Earth. It literally is.
It literally is, yeah. Yeah, there's no one alive who is older than this school, but that's fine. That's true of a lot of buildings. Okay. Okay, so we're going to talk now about, I'm going to do this in a different color, but I'm going to keep this up here for your notes as beautiful as it is. Listen. So here are some rules of relative age dating. Relative age dating rules for sedimentary rocks and for fossils. The first one is called the Law of Superposition. And this one's really easy. The Law of Superposition is super easy. Yep, superposition. Age. Relative age dating rules. The Law of Superposition. Ready? The Law of Superposition is, Hunter, the Law of Superposition. Sometimes I would preface this by saying, in an unoverturned sequence of rocks, that's rare. So I'm just going to say, the oldest rock is on the bottom. What I just said is true, but this is 90% of the truth. The oldest rock is on the bottom. The newest is where? Is on the top. This is not just true of rocks. If I have a layer of rocks, here's my sequence of rocks. Which one's, by the way, which one's the oldest here? The bottom one. Which one's the newest? The top. If I have a fossil here and a fossil here, is fossil A or fossil Z more recent? Z is more recent. We can tell because of sequence of rocks. Okay? That's the law of superposition. Yes, Dave.
Also, just a question. I saw something in Gold Rush, how the land kind of actually split on top. So if they wanted to figure out ages of fossils terrain like that, how would they do it?
Sometimes these rock layers, because of the forces in Earth, especially tipped or turned, because we have an overturned sequence of rock where actually it's completely upside down and the youngest ones are on the has happened. But that's pretty rare. So in that case, you would have to look at the surrounding area. And also, not only is it rare, but it's pretty evident. Like, you can tell if a rock layer has been overturned. You're not going to get confused about it. And the same thing with that case. Like, they would see that rock layer is not a usual one. And so then they would take those other pieces of evidence into account. Hunter, does that answer your question, Fate?
Are minerals like diamonds and gold renewable resources?
No, those are non-renewable resources. Okay, and then another one is the law of original horizontality. Horizontality. Oh, all right. That's the end. We'll get to these another time. I'll probably just put this video with the other one, like we'll have it be. Yeah, we'll see. Bye. Okay, my goal is that we're going to fuse this video with the one that we started yesterday. That, as you saw, the one that we started yesterday was not posted because I'm going to make these two into one video, and then that will be posted. So where we had left off was we had talked about the law of superposition. Do you remember that? Someone reminded me of the law of superposition. When you watch the video, it'll just look like we talked about it and then we're going to talk about it again. But so, just for our sake here in the classroom, remind me of the law of superposition. What is the law of superposition? It's a whale. A dinosaur. Do dinosaurs still exist?
No.
Yeah.
Really?
Oh, yes.
Yeah, they're birds. Birds are dinosaurs. Yes. Anyway, Kimber's gonna explain. Kimber's gonna explain the law of superposition to us.
The law of okay, it's the oldest rock is on the bottom, and the youngest rock is on the top.
Perfect. Thank you, Kimber. Let's all clap for Kimber. You know what I hate? I'm going to tell you something I hate. I hate when I ask someone to clap and instead of being nice, they just clap so hard and loud. And I thought maybe since some of us are absent, that wouldn't happen, but it still did, didn't it, Carson? It still did happen. I hate that. Okay, let's move on. Anyway, Kimmer's right. The law of superposition is that the oldest rock layer in an unoverturned sequence of rocks is on the bottom. Where would the most recent rock? On the top, generally. Okay, and we had begun to talk about the second of the, we called these the rules of relative age dating. Is that what I called it yesterday? The rules of relative age dating. And remember, we're talking here about how we can compare the ages of two different things. That's relative age dating. We're comparing their ages. One was superposition, the law of superposition. Superposition. This is really messy. And number two, we had started by saying it was what? Because original horizontality. And it is the law of original horizontality. What do you think is the root word here? We have original horizontality. What's the root word of horizontality? Hunter? Or will you have another question?
Well, I was just going to ask where the newest layer of sediment came from, like dust.
Yeah, the newest layer of sediment, like it's being put there now. You know, like if you see the wind blow some sediment, some dust or sand, onto another pile of dust or sand, that's the newest layer of sediment. You just watched it happen. You watched geology occur. That's superposition. And actually, that's one way that we know that the law of superposition is true, because we can see a new layer be deposited.
But then the sand like hardens. And
Yeah, eventually the sand can pile up and then what we call lithify, can become rock if it gets enough compression and cementation.
That someday our cities are going to be buried.
Not necessarily. There are erosional and depositional environments in the world. And depositional environments are those where deposition is occurring, where sediment is being deposited. And there are erosional environments where the sediment is being removed. And this switch, it's mutable all the time. Like if you think about the football field, on some days that's an erosional environment, and on some days it's a depositional environment. And there's a lot of factors that determine that. But the sediment isn't coming out of nowhere and burying cities. The sediment is moving from one place to another, and we call that process erosion. You might write that down. Erosion is the process of sediment moving. Erosion is the process of sediment moving. But anyway, back to original horizontality. We have here horizontal, right? We know what a horizontal line looks like. I just drew one. This is a horizontal line. Original horizontality says that when sediment layers are deposited, they are, can you guess? What position are they in? Horizontal. They're deposited horizontally. That's why it's called original horizontality. Meaning that if you come across, for instance, a canyon in Wyoming that I've been to, and the sedimentary rocks are in this shape, or if you ever go to the coffee cup at Maverick Junction on your way to Rapid City, there's that cool wall by the highway, that what we call a road cut, that looks kind of like this, like zebra stripes. Well, according to this, when these were deposited, they were all horizontal. So this must be after. What's the before look like? Well, they were horizontal. So what does that tell us? It gives us a really key piece of information. Something, probably not wind, but something had to have occurred to make it go. This is A, B, C, D, and this is now A, B, C, D. Something had to have happened. That's a key piece of information. This is how things are deposited. And if we see it like this later on, there must have been some event, probably something to do with plate tectonics. Almost always it's a large-scale event like uplift or plate tectonics, an earthquake, some kind of big shift in the Earth's crust can move layers of rock like this. Okay? That's original horizontality. So anytime we see something that's at an angle or not perfectly horizontal, some other process must have occurred. Yes? Before? After. A, B, C, D, A, B, C, D.
Horizontality.
The third one is called lateral continuity. Lateral continuity. You know what lateral means? You guys play football at all? It's a lateral pass. Fate, what's a lateral pass? Not necessarily diagonal. That's an okay way to think about it. But lateral just means to the side. It relates to the Latin word for side, which is something. I don't remember. But the lateral continuity means that it continues laterally to the side in all directions. A sediment layer. Yeah, it is. A sediment layer, thank you, Gunnar. Gunnar, the question was, is your microphone on? Thank you for asking. It is this time. A sediment layer continues in all directions continuity. A sediment layer continues in all directions. If we have some sediment layers here, actually let's start with this. Imagine we have an area that is hills and valleys. Right? So far so good. Well, according to original horizontality, if this becomes a depositional environment and the whole area gets covered with a horizontal layer of rock, well, the original horizontality tells us that even if we come along later and we can just see this little segment right here, and we can also see this little segment right here, original or lateral continuity probably is the same layer A. Layer A is continued. Even if these are the only two places we can see, lateral continuity tells us that they are the same thing because that sediment layer continued in all directions. Does that make sense? Do you have questions about this? Do you see how these are different from each other?
So I have like a bunch of rocks around my house, river rocks.
Yeah.
And I found this really like a square, and it has like tiny little like lines like these. Would that mean that the sediment just changes like really fast?
Okay. The question is basically that you have a rock kind of like this, and it has teensy tiny little stripes in it. First of all, why are there horizontal stripes at all? Which of these principles relates to that? Original horizontality. When this rock was first made, it's probably a sedimentary rock. It might be a metamorphic rock that was a sedimentary rock and then had been metamorphosed. But when this rock was originally made, it was made by little individual layers of sediment being laid down in flat lines. And not only flat, but continuous lines. And then when it became a rock, when it was squished and squished and squished to become a rock, those lines still show up. You can even tell which way was this rock oriented when it was first made. That's kind of cool. Which way? So that these were horizontal, right? It wasn't vertical. It's not original verticality. It's original horizontality.
Is that a thing too?
There's no such. I just made that up. It's wrong. But yeah, so this rock, you see, I hope maybe it just seems very apparent to you, and so apparent that it's not interesting. But I hope you understand that's what geology is all about. It's exactly what Hunter just said. You find a rock, even not a particularly cool rock, but you find a rock, and it can tell a story about the environment where it was formed. Do you see? And why is that important? Just like in your life, we can never go back to the environment that formed that rock. You can never go back to yesterday or when you were playing Minecraft as a 6-year-old. You can never go back in time, ever, no matter what. The only way we can learn about it is by finding evidence of it and applying these rules that we know are true. Okay? Does that make sense? What I just said, that whole thing is called this word, Uniformitarianism. What my geology professor called trading location for time. Because basically, we can't go back in time. So we have to trade location for that. We have to go to a location where that thing that happened in the past, in location A, is happening. So we have location A, and we find a cool rock that we don't know how it be. How it be. And so instead of going back in time, because we can't, we go to a different location where a thing like what formed object A is still happening, and that's uniformitarianism. Put another way, it is, oops, I should have this on a different mode. Put another way, it's this. The processes that have formed Earth's surface are still occurring today. We can see these things happening today. It's uniform. It's all one thing. Time is uniform. Yes? Yep.
So, since the Earth is so far away from stars that it takes years for the light to reach
Yes.
the star, does that mean that if a person were on the stars, like looking at a telescope on Earth, they could still see the
Yeah, heck yeah. Actually, I have that question has come up before on like some online posts that I've read. And the question was, if you were far enough away, and time has a certain finite speed, and you were on a planet 65 million light years away, such that the light from our planet that you were receiving back then, and you had a good enough telescope, could you see the death of the dinosaurs through your telescope? The answer is there cannot be a good enough telescope to do that. But if there was a miracle way that we had a miracle telescope that we could see Earth, you could definitely see it as it was because light has a finite. Yeah, you would be seeing Earth exactly as it was years ago.
What?
Right.
How?
Because light has a finite speed. The light you see from something like a star like Polaris is actually old. It's not what it is looking like right now. It's what it looks like 100 years ago. Well, probably not. Almost all the stars you see in the sky are in our galaxy, and they're all within probably, if not 100, then probably within 1,000 light years. And so you're seeing them as they might have been maybe back when England was being invaded by the Normans in 1066 or whatever. But that's not super old, especially not for us. Anyway, we have one last thing to talk about.
Far enough away from Earth,
Yeah.
you could see
Yeah.
dinosaurs.
Yes.
How many
If you
stars
went
are
back
But
in time,
first of all, you can't get that far away from Earth. There's no way to travel that far or that fast in space. And secondly, even if you could, there is no way to make a telescope good enough. In fact, the post that I that Hunter was why we couldn't ever make that good a telescope. And it has to do with like what all a telescope really does is gather light and then move it into a pinpoint. And you can never make a telescope the size of a universe, basically. The telescope the size of the universe could not collect enough light from planet Earth to see that far away. So that will never happen. But it is a kind of interesting thought experiment.
and the other thing is they're already dead. So
And they're already dead. Okay, the stars, no, the stars are still alive. Number 4, most of them. There are very few stars that you see in the night sky that are actually that far away. Number 4, there's a fourth one of these principles of relative age dating, which, by the way, we sometimes call these Steno's principles, after a geologist in the 1600s, I think. I've been wrong today before, though, named Nicholas Steno, and he had these ideas about geology. I think he was primarily a preacher, and he also did geology on the side. Anyway, the fourth one is called the principle of inclusions. And this one's pretty simple, I think. In fact, they're all simple. They're just sometimes it's kind of difficult to see which one is applying in which case. But anyway, the principle of inclusions is that if there are inclusions in an Earth material, the inclusions must be older than the sediment, than the rock containing them. Basically, it says if you have a chocolate chip cookie, what happened first? Chocolate chip cookies manufactured or cookie baked?
cookie baked.
The cookie got baked first, and then later the chocolate chips were manufactured.
What?
What happened first?
I thought you said cookie manufactured.
The chocolate chips cookie dough.
Cookie baked? I may have misspoken. Chips produced. Which one happened first?
Chips produced.
Of course the chips had to exist to be part of the cookie. Do you see what I mean? That's all this is. It's the same thing with rocks. If you have a with some little chunks of garnet in it, did the garnet exist first or did the rock exist first? Well, the garnet had to exist first because otherwise it couldn't be part of the rock when the rock was made. That's the principle of inclusions. It gets more complicated than that, but these are some pretty facile examples. Do you have questions about that? All of these are principles of what? Relative aging. They tell us what key piece of information about. What does it tell us about the garnets or the chocolate chips?
They're older.
Yeah, it tells us older. It doesn't say the chocolate chips are 18 years old. It doesn't say the garnets are 17 million years old. It just says older than the cookie, older than the rock. Lateral continuity tells us that this layer, or sorry, superposition tells us that this layer must be older than this layer. It's about relative age dating. Okay? But there is also a thing we call absolute age dating, and we talked about this before too. But absolute age dating, that does not mean precise. It doesn't mean exact. It doesn't mean it's always right, but it tells us an age what? Not older or younger, but what? No. It tells us what? Yeah, the value, the numerical value of the age. So here we have absolute age dating. And there are a few ways this can occur. For instance, there's a thing called lake varves, where some lakes every single year, they put one new layer of sediment down, more or less, because of the cycles in the summer and the winter in the lake. But if we find a piece of rock or a piece of sediment from that lake, we can see how old the thing is that's in that sediment, because it's 9 layers down, so it must be 9 years old. Tree rings are another way we can do absolute age dating. Trees grow one ring every year because they grow more in the the spring and the early summer, and they grow less in the late summer and the fall, and they don't grow at all in the winter. But they have rings because of that. So if we cut down a tree, we can tell if that tree was 36 years old or 450 years old or whatever. Does that make sense? Those are examples of absolute age dating. And the key here is that I'm saying numbers in years, right? I'm telling you how many years old something is. I'm not saying tree ring B is older than tree ring D. I'm saying this tree is 14 years old or whatever. Do you see what I'm saying? To go back to our example, it's not just Mr. Kime is older than Gunnar. It is Mr. Kime is 30 years old and Gunnar is 13 years old. You see? They're actual numerical ages. But the primary way we do this is something called radiometric dating. Radiometric dating, which is that there are certain things in the universe called radioisotopes. Radioisotopes decay a known amount each year. And so, for instance, if we find a rock and it has 50% parent and 50% daughter isotopes, and these are the vocab words we use for radioisotopes. The parent is the radioactive thing, and the daughter is the thing that is produced because of the radiation. If it's 50-50, we know that one half-life, what we call one half-life, has passed. And if we know that in this particular thing, in substance X, one half-life equals 16 million years, or 16 mega-annum, then how old is this? From the time it was produced, with 100% substance X, how old is it? Well, it's half parent and half daughter, so one half-life has passed, and one half-life is 16 million years, so how old is this thing? 16 million years old. This is a really easy example, but we can tell if 2 half-lives have passed, or if 3.16 half-lives have passed, or if 9.3175, whatever. We can tell how many half-lives has passed by looking at how much there be. Yeah? And that can tell us how much time has passed. Yes, Hunter?
Every rock had to be igneous to begin with, right?
Yep. You're right. And in fact, we can only really do this with igneous rocks because that kind of resets the half-life clock. When igneous rocks form, the crystals that form are 100% whatever that thing is. So the classic example is uranium-235. So if we have a mineral that contains uranium-235, we can later compare how much of that uranium-235 is still uranium-235 and how much is lead. And we know the half-life of uranium-235, and so if we look in this rock and we see 75% lead, 25% uranium-235, we know 2 half-lives have passed, and we know the half-life of uranium. And so we say, this rock is this many years old. That tells us an actual number in years. And then here's the kicker. We combine this with the relative age dating from before, and we say, this rock layer, maybe we can't date these. Maybe we have rock C, D, E, and F. And the only one we can date is C. The rest of these don't have the stuff we need. But we date C to be 1.7 million years old. Well, what do we know about layer E? Well, it must be younger than 1.7 million years old. So say we find a nautilus fossil in layer E. How old is the nautilus fossil? Well, we don't know exactly right now, but we know that it's less than 1.7. And then maybe layer G up here, we date to be 0.9 million years old. So now the nautilus fossil is somewhere between 0.9 and 1.7 million years old. Do you see? We use all of this together to tell us about Earth's past. Why? Well, we can't learning about China or Burma or whatever in history class. We can't send newscaster. What's the newscaster I'm thinking of his name? Anderson Cooper. We can't send Anderson Cooper to 0.9 million to ask him what he thinks about it. You see what I mean? We have to do this kind of stuff. We have to use our evidence to learn about the past because we can't go there. Do you have questions about that? Have you been reading your explorations so that you know about this too? All of this should be review because you read your explorations. Is that correct? There's more detail in your explorations. Should you still read them? Yeah. The quiz is going to be tomorrow. You don't have any questions about this, but Will has one. What is it?
So is the one full life?
No, we call it a half-life because that's how long it takes for half of it to decay. The thing itself is just called half-life, and the symbol is this Greek letter lambda.
Just deteriorate, not decay.
Either one. It decays. It goes from one thing to another, so we call that decay. Fate.
So
Very good,
What?
Hunter. I'm glad you could come up with that, Gunner.
It was 75% lead and 25% then you said
That's yeah, because what happens is after one half-life it's 50-50, and then after two half-lives, the parent isotope. This is a gross diagram now. Sorry. Okay, so 0 time has passed. It's all one thing. Okay. After one half-life, it's 50-50. After another half-life, it's 25-75. After a third one, it's 12.5% this and 87.5% the other. And then another one, we just keep halving this little bit. Does it ever fully decay? If we keep halving something, if we start with 100 and half it, can we ever get to 0? No, it's an asymptote. Asymptote, bye!